The main reason we learn the intermediate value theorem in calculus AB is so that we can justify intervals where functions are increasing and where functions are decreasing. That's why I include this in Unit 3, Lesson 2, which is still about the mean value theorem. So you need to be able to find and justify intervals where a function is increasing and intervals where a function is decreasing. This will lead to being able to justify local maximums, local minimums, and then we're also going to get to concavity pretty darn soon. Okay, so increasing and decreasing, well, everybody thinks those are pretty easy words. I don't know, sometimes people get it confused, and this is a pretty easy question. Is f increasing at x equals 3? And the answer is, well, no, of course not. F only has, 1 point, and it's at x equals 3. You really can't answer that. That's kind of ridiculous. Likewise, people have no problem with this if they're saying yes and no. Is f increasing at x equals 3? No, of course not. That graph is going down. But that's not really what we're at here. Because if I give you this graph, is f increasing at x equals 3? Most of you think, yes, of course f is increasing at x equals 3, but it's not, because all three of these situations match. The question is, if you're only allowed to consider x equals 3, is this graph increasing? Is this graph decreasing? No, because a function can't increase at a point. So that's actually the same answer here. No, f increases, but this very specific question, is f increasing at x equals 3? No, f can't increase at a point. So that's like a super common error. And actually there was something weird, because last year's AP Calculus AB test had a question that was kind of worded. Well, don't worry about it. It was kind of worded where it was talking about increasing, decreasing at a point. College Board used to make a really big deal about that. But anyways, a function can only increase or decrease on an interval. So the more precise way to say that is, well, while f isn't increasing at x equals 3, f is increasing on an interval containing x equals 3. That seems pretty unsatisfying because it doesn't say which interval, but you're allowed to say this, saying, kind of like when you're doing a limit and you're getting arbitrarily close to an input, some interval near x equals 3, a little bit less and a little bit more, f increases on that interval. Oh dang, I changed it. And really what we mean by increasing, maybe a better way to say that is, the larger x value, you have to have a comparison here. A function increases if the larger x value corresponds to the larger y value. So again, this kind of pops out of the mean value theorem. If we have a continuous function, I need something darker here. If we have a continuous function and we have a positive first derivative on the interval, right? So we're like, hey, this thing's positive. Well, what must be true is that f of b minus f of a, or the y value at the end minus the y value at the beginning of the interval, that would be a positive difference. And so if that first derivative is positive, then f of b is larger than f of a, the y value. The y value at the right-hand endpoint is going to be larger than the y value at the left-hand endpoint. And so really what we get to conclude in shorthand is that a function increases on the interval a to b if that function is continuous and you have a positive first derivative of that function for all x's on that open interval. We'll have to watch out for the endpoints because there's a little bit of weirdness there, but devil's in the details. And then maybe we have a picture for that. So if we know a function is, it's actually a biconditional. A function is increasing on the interval if the first derivative is positive on that interval. And if the first derivative is positive on that interval, then the function increases on that interval. We can go both directions. And then pretty obviously, a function decreases on an interval if that function is continuous and that first derivative is negative on that interval. So let's see what an example looks like. And if you've followed along here, extreme value theorem, a lot of this is pretty straightforward. The first thing we need to do, if we want to know where a function is increasing, where a function is decreasing, we need to consider continuity. And that one's pretty easy. X squared is a parabola, that's all. That's our favorite parabola. And x squared is a polynomial, so y equals x squared is continuous and differentiable everywhere. Great place to start. So if we're going to look for this function increases and decreases, we need to know about the sign of its first derivative, so we'll find its first derivative. Y prime is 2x, and then we're looking for critical values. Critical values where a derivative is equal to 0 or undefined. And the reason that's now even more important is, a derivative being equal to 0, or heck, let's go, any function. How can a function change from being positive to being negative, or negative to positive? Two ways. That function could be equal to 0, or that function could be undefined. So we're kind of thinking that in our head. We're not really graphing the derivative, but where can the graph turn around where the derivative is equal to 0 or undefined? So we just get x equals 0. Now I have this pre-made, but there are a couple of details I want you to know. So since the domain of x squared is all real numbers, we're going to have arrows on the ends of this thing we're making called a sign chart. We're going to put all critical values and all domain problems on here. So that's just x equals 0. We're going to write a little x on the right-hand side saying, hey, these are x value inputs. And we're going to label our sign chart. In this case, we're going to call it the sign of y prime. The reason we need to label, well, you need to label everything, but also later on you'll make sign charts for second derivatives. Anyways, so it's in the name. All we need to do is find the sign of y prime. So choose any number less than 0. It could be -1, -10, doesn't really matter. When you put that into y prime, 2 times -1 is negative. We don't actually care about the number. -5 times 2 is negative. 2 times -1,000,000 is negative. So all of these x values less than 0, if you put them into y prime, we would get a negative number. And remember, a negative first derivative is going to indicate that the function, in this case x squared, is decreasing on that interval. So I will, underneath that interval, do a little line segment with a negative slope to give me a visual indication of that. So choose any positive x value greater than 0, right? And 2 times 1, 2 times 10, right? We're putting those into y prime. We get a positive, which means y prime is positive that interval, and x squared increases on that interval. Okay, I have a prettier version, so I'm going to delete that. Okay. So then we actually have to write out what we see. And that is, well, I already said x squared is continuous, but I'm going to say it again here in my conclusion. And the reason is it's so gosh darn important. And if you say that at the beginning and at the end, number 1, you'll probably remember one of them. And number 2, you're kind of training your brain that that's important. So anyways, y prime is greater than 0 on the open interval -∞ to 0. Why don't we include this endpoint 0? Well, because y prime isn't positive at 0, y prime is equal to 0 at 0. We did that work when we were looking for critical values. Okay, and then we say, so y equals x squared decreases from -∞ to 0. But notice we do include the right-hand endpoint 0 here. And that bothers a lot of students because really of an incomplete definition of decreasing. So let me put a few very specific ordered pairs on this x squared graph. And so if you choose any of these, let's say this one and this one, when we say decreasing, what we mean is choose the larger x value and make sure it has a smaller y value. And of course that's true for this pair, and it would be true for this pair. And it doesn't really matter how you mix and match. No matter what, all of these points, the one on the right has a smaller y value. I don't know what I did there. Uh-oh. Oh, I hit a magnifying glass. Okay. So let's just put a few more points on. Obviously, that point has a lower y value, lower y value, lower y value. And I guess the question is, does this situation where the lower y value on the right, does that include x equals 0? And the answer is yeah, of course it does. And that's going to lead to something called the first derivative test soon. But we include that endpoint. And then it's going to get slightly worse here in your mind if that didn't make complete sense, because what we're going to say, we also have to include where x squared is increasing. Y prime is greater than 0 on the open interval, 0 to infinity. So y equals x squared increases on the interval 0 to infinity and including 0. And the reason I say it gets worse for some people is it really bothers some students that 0 is included when x squared increases and when x squared decreases. But that's not the right way to think about it, because you're thinking of x equals 0 as a point. No, there's this interval where you can say, hey, x squared increases, and you're going to include x equals 0 and all the numbers to the right. And you can see that if we put a dot here where x equals 0, any point to the right, no matter how close it is, will have a higher y value. Okay, so first example done. So also watch out. I'm carefully choosing the words I'm writing down, and nothing is superfluous. Logically, people don't like to say y prime is positive on this interval, so x squared decreases on that interval. They just want to assume that we're filling in the blanks, but you actually kind of need to do that double talk to be as precise as we want. Like we were talking about, watch out for the endpoints. We're going to include the endpoints for a continuous function when we say, hey, this graph is increasing on this closed interval, but we have to watch out for continuity as well. Okay. I think this is a pretty easy example, so we'll just kind of roll through with a little bit less detail than the last. Where is f of x equals e to the x increasing, and where is it decreasing? And then we're going to justify. And so we know the graph of e to the x by now, which means we know, well, the work's going to be pretty boring because e to the x is always increasing. While I'm thinking about it, we better make sure we address the decreasing question. We can't just say, hey, e to the x increases everywhere. We need to say, and e to the x decreases nowhere, or something like that. So we'll start off thinking about continuity. F is continuous and differentiable. E to the x is not a polynomial, but that's a known fact. If you know the graph of e to the x, it's a smooth and continuous curve, so we can just state continuous and differentiable. So next we'll find the derivative. The derivative of e to the x is e to the x natural log of e. And we know, because e to the x is never equal to 0, that its derivative, also e to the x, is never equal to 0, so we'll just write that. I'm not going to write that f prime is never undefined, because I also already kind of said that when I said f is differentiable. And so my sign chart is pretty boring as well. Remember, we want arrows at the end of our sign chart because we have a domain of all real numbers. We have this little x down here saying our input is an x, and this is the sign of f prime. And you can tell, based on the graph of e to the x, any input, 0, 1, 2, 1/2, choose a weird number, gives a positive output. And so how are we going to start our conclusion? F is continuous. F prime is greater than 0 for negative infinity to infinity, so f increases on negative infinity to infinity. Always open intervals there. F prime is never negative, so f does not decrease. So here we're throwing a little monkey wrench into the plans, and that is k of x is 1 over x squared, and hopefully I wrote it first. X cannot be 0. That's not part of the domain, which means at the end, well, we'll get there. So k of x is continuous everywhere k is defined, and that's from negative infinity up to 0, not including 0, and just to the right of 0, all the way to infinity. So that first derivative, pretty straightforward, negative 2 over x cubed. Hopefully you have that memorized by now. And we can tell k prime is never equal to 0, right? Because that would be setting the numerator, negative 2, equal to 0, and of course that can't be true. And then let k prime be undefined, that's the denominator equal to 0, and we get 0. So how are we going to make this sign chart? Well, we actually kind of knew 0 anyways. So negative infinity to infinity, this is an x. We're doing the sign of k prime of x. We'll put 0 on there. And so, let's see. Any number less than 0, negative 1, well, remember, we're putting negative 1 into k prime, so negative 2 over negative 1 cubed is negative 2 over negative 1, that's positive. And then choose some number greater than 0. And that's, I don't know, put in 1, we get a negative. So 1 over x squared increases from negative infinity to 0. Ooh, I forgot my 0. And decreases from 0 to infinity. Okay, but notice, well, again, we start off with k is continuous on negative infinity to 0 and 0 to infinity. K prime is positive on negative infinity to 0. We can't include 0 here because, well, 0 is not part of the domain of k, which is also why we say k increases on negative infinity to 0, but not including 0. On the last one, we had a bracket here, and we can't include that because, well, x equals 0 doesn't spit a y value out of k. Likewise, k prime is less than 0 on 0 to infinity, so k decreases on 0 to infinity. And then here's a graph. Notice I didn't put the graph in first. I put it at the end just so we could make sure, I don't know, that we're paying attention to the details, not just kind of memorizing. Because I think if I had that graph there, you'd know we wouldn't include the endpoint, but who knows? You're watching this on the internet. I don't know what that does about. Where is g of x, 2x cubed plus 3x squared increasing? And where is it decreasing? So, you know, we're kind of expecting something like this. So we're expecting an increasing interval, a decreasing interval, followed by an increasing interval. Now, g of x is a polynomial, so g of x is continuous and differentiable everywhere. Let's write that down first. And then we want to find critical values, so we'll find g prime. 6x squared plus 6x. We're going to let g prime equal 0. And we do some algebra there. We're also going to note g prime is always defined. You don't have to write that, but I think it's good to remember. So 0 equals 6x squared plus 6x. 0 equals 6x times x minus 1. So we get x equals 0 and x equals negative 1. So I'm already thinking, I kind of know where my answer is going to be. I'm going to end up, or at least I should, having g prime positive for x values less than negative 1, just because I know the shape of graphs like g of x. Likewise, negative in between negative 1 and 0, and g prime is positive for x values greater than 0. So we make a sign chart. And of course, that's what we get. And, well, maybe let's slow that down. Negative 1, 0, these are x's, and we're going to say the sign of g prime. Okay, so, you know, up here g prime, I'm actually going to use that for two places to substitute, and that is a number greater than 0. If you think of a number greater than 0, most people will say 1, but I'll say 1,000,000, because 6 times 1,000,000 squared plus 6 million is very obviously positive. And so g increases from 0 to infinity. Likewise, choose a number less than -1. You might as well go for it. -1,000,000. 6 times -1,000,000 squared is going to be positive and overpower 6 times -1,000,000. Now, when I choose a number in between -1 and 0, I guess -1/2, even though this is set equal to 0, we know 0 is equal to, I'm sorry, not 0. I'm thinking of this as g prime of x is equal to 6x times x minus 1. And because all we care about is the sign, well, 6 times -1/2 is negative. -1/2 plus 1 is positive. A negative times a positive is negative. I think that's the best way to go. Okay, erase that. And then what are we going to start off with? G of x is continuous. G prime is positive on -infinity to -1 and on 0 to infinity. A big mistake would be to use a union here. We don't want to get in that habit, at least at our school. We're not real strong on set notation anymore because we've kind of accelerated everything, so that's one of the things that got a little lost. But just, I don't know, maybe trust me on that. Anyways, so g of x increases on -infinity up to including -1. Notice closed endpoint here. And on the closed interval from 0 to the open endpoint infinity. G prime is negative on -1 to 0, so g of x decreases on -1 to 0. I wonder what happened to my pink 0. Wait, does it pop up? It doesn't. Okay, so I will actually make another video about those. You do not need to see those today.